A naught is the slope of the 2D section. Now, for different airfoils, you'll have different graphs to get them. But since I think it was found in one of the examples, you don't need to get it for the same airfoil. It's already there in one of the examples. I think 6 or 6 point something.
And I took it from the example.
That's fine. You don't need to find, but at least you should know how he found it, so that if you have a different airfoil, you can find it. And actually, we are going to see it today in one of the problems that we will solve today. I'm going to do this.
Okay. Shukran.
Okay. Any other question?
Doctor.
Yes.
I have a question in turbojet engine.
Okay.
Inside the turbojet, we have compressor and burner and turbines.
Yes.
The volume of these parts, it's there is a relation between this volume and the pressure inside the turbojet engine.
What do you mean by the volume? You mean the diameter?
العلاقة بين الفوليوم والبرشر مثلا في المساحة، هي في المساحة يعني أقصد.
cross section area بتاع of the engine.
ما اسمعك دكتور، صوتك قطع.
The cross section area of the engine.
لا أنا أقصد داخل الكمبرسور يعني.
Okay, let me share this slide and see if I understand your question correctly. Okay, so that's the turbojet engine. You see it?
No,
do you see the slides, Ishwa?
Yes, we can see.
Okay, so this is your question. Your question is, if I get it right, is there a relationship between these dimensions, the diameters here, and the thrust? Is that correct?
الشاشة عندي ما تطلع أنا.
الشاشة.
أيوة الحين طلعت. أيوة الحين ضبطت.
Okay. So you're asking, is there a relationship between these dimensions here, the diameter, for example, and the thrust of the engine?
Yes.
Okay. Yes, the answer is yes, there is a direct relationship. And we are going to solve a problem on this in just a few minutes.
Okay.
Okay?
Okay, okay.
Any other question? We will solve a problem right away. That should answer your question.
Okay, thank you so much.
Okay. Actually, let me take that snapshot. I might need it over there since you brought the issue. Well, I have one there, but that might be better than the one that I had. Okay, so now we are at the slideshow, unless anyone has another question. What we will do today, inshallah, is that we are gonna solve problems. Today is basically a problem solving session on chapter 2 as well as on chapter 3. So we will look at example 2.12, which is slightly different from the homeworks that you had. Then we are going to solve problem 3.1. And why we are solving problem, not an example, because practically there are no examples in chapter 3. It is basically a qualitative discussion of the types of the engine and a list of all the equations required for different types of engine. Then we will conclude by a summary sheet of the text from the textbook of equations of chapter 3. One of you have asked for such a sheet. I just wanted to show it from the textbook. Okay. Feel free to stop me at any time as we go through the examples. So we will start with the example 212, and this is the one, not the first one, that's the second one. It reads, consider the wing described in example 2.5. So you can see in the top here, I'm just reminding you of example 2.5. This is 2.5 on the top. Pretty sure you guys are now familiar with example 2.5 because it's basically very close to the homework problem. So let's go to 2.5 and read it. It says it has a straight wing aspect ratio 6. That's not the one that you see in the drawing. It's a straight wing. That means it's not swept. It's not swept backward. It has an aspect ratio 6 with a NACA 2412 airfoil. That's the airfoil you have the data for in your textbook, chapter 2. And over there, it had an angle of attack 6 degrees and the span effectiveness was 0.95. Can anyone remind me what is that span effectiveness? What's the 0.95? Span effectiveness. Anyone?
دكتور بس ايه السؤال انا ما سمعتك والله الصوت قاعد يقطع عندي.
شباب, do you hear me correctly? Is it my problem or it's on his side? Can anyone confirm?
I think it's on his side because I can hear you quick.
Maybe you can move
clearly.
closer to the antenna of the Wi-Fi. Okay. So the question is, what does E1 equal 0.95 mean? What is that? What's the span effectiveness factor? What does that mean? Anyone? A span effectiveness factor is basically a number that represents how effective is the 3D wing compared to the 2D one. A span effectiveness factor of 1 would give you the lift distribution of a 2D wing. Okay, so 0.95 is close to that one. So the span is very efficient. E equal 0.95. Okay. Now, the problem that we are solving now says it's the same wing, except that it has a sweep of 35 degrees. So the wing is swept backward at an angle 35 degrees. That's the one measured between the half chord line and the reference line. And it's asking you calculate the lift coefficient when at low speeds for this 6 degrees angle of attack. And he wants you to compare it with the straight wing that we had in problem 2.5. So basically, if I have a straight wing and a swept wing and everything else is the same, what is the change in lift coefficient? That's the question. Now, before we solve the problem, let me just check if anyone can tell me which one will have higher CL, the straight wing or the swept wing?
The swept one.
Well, the answer is the straight wing. The straight wing will have higher CL than the swept one. And why is that? This is because air actually is coming along the reference line direction this way. So if the wing was straight, the sections would see all the coming air. But here you see the sections are inclined at the air. So there is going to be like a cosine of an angle. And that will reduce the CL a little bit. So swept wings will have less lift than straight wings. And that's always the case. If everything is the same, swept generate less. So why do we sweep wing if that's going to give us less lift? Because we want to reduce drag. We worry more about the drag here. We don't worry about the lift because an aircraft with a swept wing will fly very fast that it will generate enough lift. Okay, so the increase in lift will come from the speed, not from the wing itself. Swept wings decrease lift. Okay, remember that. Because later on in chapter 6, we will be selecting the type of wing. How would it look like? So depending on the speed, you will choose the type of wing that we have. Okay. So let's solve the problem. It asks you what's CL. And if you have solved the homework, basically you find the CL by finding the slope, that's A, and then you multiply by the angle of attack. And that's what we will do here. Now in the textbook, you have a set of equations for different slopes depending on low speed, compressible, supersonic, and so on. Okay? So we have to pick the right one for this problem. Low speed swept wing. So we go to the equation of low speed swept wing, equation 219, if you are following me with your textbooks. It says the slope of the lift curve equal the slope of the 2D section, the airfoil, cosine the sweep angle over some expression. And you see here the term A naught cosine lambda over pi aspect ratio is repeated here and here. Here it's squared, here it's not squared. So it would be wise for you to calculate that term on the sides on a piece of paper and then use it rather than calculate it twice. Now, let's see what do we have in here. We have, of course, the sweep angle, 35 degrees. We know this one. We'll need the slope of the the slope of the 2D section. So we get this from the figure. And you have been asking about it now. So if I want to get A naught and it's not found on any airfoil, all I need is the slope of that line. So you pick any 2 points along the straight line that are away from each other. Then you calculate delta y over delta x. That means delta CL over the angle of attack. That would be the slope. However, be careful that the angle of attack here is in degrees. The horizontal axis is in degrees. So if you want to get A naught that you are going to calculate, you need to convert it to radians. And the conversion from degrees to radians is 57 degrees for each radian. 1 radian is 57.3 degrees. So if you calculate delta L over delta alpha in here, that will give you the slope. Then you need to multiply that by 57.3. Okay, that will give you 6.08. And just to give you a perspective of that number, typically the slope of the 2D section is very close to 2 pi. Pi is 3.14, 2 pi is 6.28. You see that the slope is 6.02, very close to 2 pi. So we have A naught, we have the sweep angle, we know the aspect ratio 6 is given. So if I calculate this whole term here or that term, because it's the same, it will be 2.62. So this 2.62 is not given, it is that term, A naught cosine over pi aspect ratio. If I substitute, I will get 3.8. What is this 3.8? It's the slope of the swept wing, CL alpha curve. It's CL alpha of this airfoil, of this wing. And as you can see, it's 3.8 per radian. Remember the 2D section, the one that you see here on the side, was 6 per radian. So you see it dropped a lot. It lost like 40% of the slope, simply because of the finite as well as the swept factor. Now, that's the slope. I cannot take this slope and multiply it by 6 degrees because this is 6 degrees and this is the slope per radian. So I have to convert it to be per degree. So we will take the 3.8 divided by 57, giving me the A per degree, 0.066. Now I need to multiply it by the angle of attack in order to get the CL to be 0.54. Please be careful here. When you multiply the slope by the delta alpha, remember that if you have the curve beside you now in your textbook, if you look at the curve, it intersects the x-axis, not at 0, the 0 is here actually, it intersects at minus 2.2. So if you want to get CL, I cannot multiply by 6 degrees. It has to be 6 degrees and 2.2. So 2.2 plus 6 degrees, that's delta x. Multiply by the slope will give me delta y. So it turns out to be 0.544. Okay, so although I started with a 2D section with an airfoil that would give me at 6 degrees, it will give me like 0.8 something, maybe 0.9. We ended up with CL just 0.54. We lost some of the lifts because of the finite wing in here. We lost some of the lift because of the sweep angle in here. So instead of getting CL just like the airfoil of 0.8 or 0.9, we just had 0.54. Is this clear? Everyone, any question? Okay, so the second part of the question was compare this value that you had, the CL, to the CL that I would get from the unswept wing from problem 2.5. Now we're not going to calculate it here, it was already calculated in 2.5 to be 0.64. So CL is 0.64. Now I need to emphasize the difference between three numbers here. That should be very clear in your mind. If I go on the 2D section and I at 6 degrees, this is 0. This is minus 2.2, this is 0, 2, 4, 6. If you comment 6 and you read the CL, it will be 0.95. 0.95 is the lift coefficient for the 2D section. When the 2D section was formed into a finite wing that is straight, that's the first problem, the lift instead of 0.85 became 0.65. When we swept the wing backward, just like this one, it went even lower and it became 0.54. Okay, so now you see the effect of each of the span, finite span, as well as the sweep angle. Both would reduce the lift from what you had in the 2D section. So the decrease was about 16% for sweeping the wing backward. Okay, Shabab, any questions?
Doctor?
Yes.
Now for the previous example, which is 2.5.
Yes, that's the one.
The wing was straight, right?
Right.
So why does it differ from the CL on the graph?
Very good. Very valid question. Can anyone answer this question? His question is, we had a straight wing that was not swept. So why it's different from the one that we had on the graph? Why it's different from, let me go there, from this one? Why it's different from what we read at 6 degrees in here? Can anyone answer the question? No raised hands? I just explained it. I'm not talking to you, I'm just telling them that I just explained it. So why would it be different? Okay, the 0.8 that we get from the graph is for the 2D section. What do we mean by a 2D section? What's that lift? That means it's a wing that's extending, of course, ideally, from infinity to minus infinity. That's a 2D wing. So the air flowing around the wing doesn't feel the ends of the wing. Okay, all sections are the same. There is no wing tip vortices which would reduce that lift. Remember the wing tip vortices that we talked about a couple of lectures back. So this figure doesn't have ends for the wing. The wing doesn't end here, it's just going to the right and going to the left. So we should expect that lift to be high. So it's 0.9. Now for the straight wing, for the straight wing, section example 2.5, it was straight, but it was finite. It has an aspect ratio of, what is that? 6. So the length, the half length of the wing is 3 times the chord of the wing. So it was finite. When a wing is finite, air tends to move from the lower surface to the upper surface and would start to circulate, causing the wing tip vortices, which has a downward component, pushes down on the wing, reducing CL. Does this answer your question?
Yes, thank you.
So the reduction to the 0.648 because of finite wing. The reduction to 0.54 is because of the sweep. Okay, now, so I really don't care about the numbers or the equations. You don't need to worry about the equations because they will be there in any quiz or exam. You will have a formula sheet with you. But I need you to understand the effect of each of these parameters. Because once we start to make design, you will select these parameters. You will select the sweep angle, you will select the aspect ratio and so on. So in your mind, you must know what do they do to the design? How would they change the performance of the wing? So now we know they both reduce CL of the wing. Any other questions? Okay, so now let's move on to the second problem. This is problem 3.1. It reads the General Electric J79 turbojet, that's the one. That's the engine, very famous turbojet engine from the 1960s that used to power fighter aircraft at that time. So it used to power that F-104 starfighter. And it's actually the predecessor of the J100 that's used to power the F-16. So this turbojet engine produces a thrust of 10,000 pounds at sea level. So if it runs at sea level conditions, it has a 10,000 pound thrust. The inlet diameter is 3.19 feet. Now to your question. You talked about the dimensions. Would it affect the thrust? So let's see. So the diameter is 3.19 feet. That's about 1 meter, roughly 1 meter, the diameter here. Now, if you are not very much familiar with the pound as a force, with the foot as a length, with the slug as a mass, it's about time you start getting to know these dimensions, because in the industry, British units are still widely used. I would say even more than SI units. So pound force is the unit of force. Feet is the unit of the length. So if the airplane, which is equipped with this engine, is flying at standard sea level, so almost close to the ground sea level conditions, that means it has a certain temperature, certain pressure, and certain density for the air. If you have received your textbook, flip the pages to the appendix and the end, and you will see the standard atmosphere table, where you have density, pressure, viscosity at different altitudes. So at 0 altitude, that's the sea level, this engine, which generates 10,000 pounds of thrust, the aircraft will fly at a velocity of 1,000 foot per second. Is this a high speed or a low speed? 1,000 foot per second.
High speed.
Yeah, if I ask you roughly, what's the Mach number for 1,000 foot per second? Roughly, just give a rough number. Is it close to 1, close to 0.5, close to 2?
Close to 1, but it's less than 1.
Perfect. Yes, slightly less than 1. So I would say 0.9 maybe, or something, very close to that. Okay, so 1,000 foot per second, that's the velocity of the aircraft. And we are required to find two things. One, the jet velocity. So the jet that's exiting from the engine, what's the velocity in here? We need it relative to the airplane. Remember, the airplane is moving forward with a speed of 1,000 foot per second. That means air is entering the engine with 1,000 foot per second. But it's exiting at a higher speed. The question is, what's that higher speed? Okay, that's the first question. The second, find the propulsive efficiency. If you remember last time, we defined the efficiency of a turbojet engine. We derived actually the expression of the efficiency of the engine. Okay, and we're going to talk about it when we get to the second part of the problem. Is the problem clear? Okay, so let's see. First, we have the thrust, we have the speed, and we have the diameter. These are the only pieces of information that we have. So we have to figure out an equation that would relate these. Now for the turbojet engine, if you remember the summary we had in the last slide last time, we had only two equations. One of them gives me the thrust from Newton's second law. The thrust is equal to m dot multiplied by the change in velocity across the engine, v jet minus v infinity. If I take v jet minus v infinity, which is the speed at the entrance of the compressor, roughly, if I take these, the difference between these, and we call it v1, so v1 is the difference, v1 is the relative velocity of the jet compared to the speed of the aircraft. If I take that speed and multiply it by the mass flow rates, m dot of the air, how much air enters into the compressor and the turbine, that would give me the thrust. We had that equation last time. Basically, what you see here is Newton's second law, because it says, remember F equal ma? That was correct when the speed was changing and the mass does not. Here, it's F equal m dot v, because the mass itself changes with time that we have in here. So how in a unit time, what's the value of the mass that's passing in a certain period of time? Let's say 1 second, that's the m dot. So for gases, Newton's second law takes that for m dot times that change in velocity. So this would be close to the answering the question that we had, would the size matter? Yes, the size would matter, the volume would matter. The larger the diameter, the more mass flow that will pass through the engine, the more thrust that I will have. It's directly proportional to the cross-sectional area. In fact, we have an expression for the mass flow rate here, m dot. M dot for a gas that's flowing through a closed, through a pipe, for example. We call this type internal flow because it's going inside something, not external, just like the airfoil. M dot is rho times A times V, where rho is the density of the air, A is the cross-sectional area of the tube, and V is the speed. So as you have just asked a few minutes ago, would the diameter affect the thrust? Yes, the diameter. If you double the diameter, you have increased the area 4 times, the cross-section area 4 times, because it has d square in there. Then you have increased m dot 4 times, and that means you have increased the thrust 4 times. It's as simple as this. If you have two engines, one of them has a double the diameter of the other, it definitely has 4 times the thrust. Okay. Does this answer your question? Who had the question a few minutes ago? I think he's just left us. Okay. So let's now see what do we have. It says the engine is running at sea level conditions, so we know the density. And from the Appendix A in your textbook, the density in British units is 0.00237. Please don't mistake that with the one that you probably remember, 1.125 Newton per, or sorry, kilogram per meter cubed. Okay, because that's a different unit. And the unit here is slug per cubic feet. If you use the slug, if you use the foot, if you use the pound, there is no conversions. You don't need to convert anything. Just use them together as a British system, and the result will come out to be correct at the end. Just like when you use meter, kilogram, Newton, you don't do convert anything, and the result will be correct at the end. So the density is 0.00237. The area of the engine, I can calculate that from the diameter. The diameter 3.19, so the area is pi over 4 times the diameter squared. And the speed here is the same speed of the aircraft, because if the aircraft is moving forward with 1,000 foot per second, air is moving backward with 1,000 foot per second. So the speed is 1,000. If you crunch the numbers here, and m dot will turn out to be almost 19 slugs per second. Every second, 19 slugs of air will go through that compressor and through that nozzle. Now that's considerable amount. I will leave it to you to convert it to kilograms and see how much is that in kilograms per second. Now that we have m dots, all I have to go now is to put it in Newton's second law. That's the second equation. We had only these two equations. For a jet engine, F equal m dot V and m dot is rho LV. That's it. Don't have any other equations. So I will take m dot that we have just calculated, the 19, and I will put it here. Remember, I know the thrust to be 10,000. The only unknown here is V1, or the change in the speed. V1 is V jet minus V infinity. Okay, so if you do this, that would be 10,000. That's the thrust divided by the 18.997 gives me a V1 of 526.4. What does that mean? 526.4. That means the relative velocity of the jet compared to the entering air is 526.4. The speed here is 1,000. The speed here is 526.4 more than the 1,000. So it will be 1,500. It will be 1,526. The speed here is 1,526. It has increased by 526.4. Okay. Any questions for the first part of the problem? First part, find the increase in the speed. We found m dot, we found from the thrust, we found the increase in the speed. Okay. The second part says, what is the propulsive efficiency? Now, can anyone define the efficiency that we had last time? Not the equation. Well, the equation is simple to remember. You will remember it once you solve one or two problems. But I need the definition, the meaning, physical meaning of the efficiency that we had last time. When I say the efficiency of this engine is 60%, what does that mean?
This is the amount of power generated.
That would be in the denominator. So that would be good. That's good. That's 50% of the definition.
The ratio of the generated versus the actual power you have.
Well, I will change it a little bit. I would say the ratio between the useful power to the generated power, because not all the generated power has been used to provide thrust. So in the engine, in here, there was power that was generated here by the burning in the combustion chamber. Not all that power translated to thrust. Why is that? Because some of this power has been lost simply to increase the speed here. If you take a snapshot to the air in here, it has a speed of 1,000. If you take a snapshot to the air in here, it has a speed of 1,526. So you have paid for that air to increase speed. You have paid the price. We made it have more kinetic energy. So this is a sort of lost energy that we did not use. We used it when it was here, but once it's out there, all the energy that he gained is a lost energy. Okay, so efficiency we defined last time as the generated power in the denominator and the useful power in the top. What's the useful power? It's the thrust multiplied by the speed. This is what actually reached the aircraft. The thrust multiplied by the speed. Then when we derived it last time, we just made some simplifications and we reached out a final expression that I would like you to remember because it's a really simple one. This one we derived last time. Go back and check the derivation. It says the efficiency of any propulsive system that use jet is 2 over 1 plus V jet over V, which is V infinity, of course. of course, times 100 because it's a ratio and percent. And that's it. So for this problem, VJet was 1,526, which is rounded here to 1,530. And you probably now know that in the textbook, the author rounds all the number to 3 significant digits. And the reason for this is that 3 significant digits is as many digits as an engineer would need for reasonable accuracy. There is no point in using a 4th digit or a 5th because the theories that we are using are not that accurate. So by maintaining 3 significant digits, we have reasonable accuracy, 1 in 1,000. So anyways, you can use the 1,526, of course, and the result will almost be the same. We know VJet is at 1,526, and we know the V to be 1,000. Now you substitute here and we'll get a propulsive efficiency of about 79%. 79. So the energy generated here, 80% was used to provide the thrusts of the aircraft and 20% were lost to the air, and the hot air carried that energy with it as it moved out back through the back of the engine, through the nozzle. We lost that energy. Okay. Now 79% is not very bad. It's reasonable. It was very good in the 1960s, but now it's not as good. Okay. Is this clear? Okay. Now let me ask you a question. What if the same engine is now fixed, but not on that fast aircraft that flies at 1,000, but on a slower aircraft that will fly at 500 feet per second? So I will take that jet engine and I will put it on a slower aircraft, a bomber, for example, or a cargo aircraft that goes slower. What do you expect will happen to the efficiency?
Excuse me, doctor.
Yes.
Dr. Wael, is this there is an error or it's right? It says 1016.4.
Where is that? No, that's a typo. That's definitely, it's 26. What was the number? 26, 1526. Oh, thank you. No, that's a typo definitely in the test. Because the speed is 1530 or 1526. That's a typo. But the final answer is correct. If you do the math, the final answer is going to be correct. Okay, 78, 79, something like that. Okay, so I will correct that. Thank you for bringing it to my attention. So back to question. If VJet increases, if we take that engine and we put it on an aircraft that's slower, that means instead of the 1,000, the speed is 500. What do you expect will happen to the efficiency? Would it go up or down?
It will go down.
It will go down, correct. Because if V goes down, then this ratio will increase, and since it is in the denominator, the whole thing will decrease. So the efficiency will go down. Now that brings us to the discussion that we had last time when we were talking about when to use jet engine, turbojet, when to use turbofan, when to use turboprop, and when to use a piston engine or reciprocating engine with a propeller. And we said we use the appropriate one to each flight regime. You see, turbojets are okay when the speed is very high. It gives me good efficiency here. But if the speed becomes low, then the efficiency of the turbojet will go down. It will still give you the thrust, but at a lower efficiency. So it would not be wise to put a turbojet on a slow aircraft. Maybe if we use a turboprop, in that case, for a speed of 500 feet per second, then it will have very good efficiency if it was a turboprop.
Dr. Wael,
Yes.
For the V, I mean, it's gonna change also because we have to recalculate it. So
That's correct.
It's supposed to be the same, right? For the efficiency.
No, it will not be the same. If V goes down, Vjet, because if you go here, the V1 itself will change.
Yeah.
So if you calculate here, this is the thrust, this is m dot, you go to m dot will change by itself because the speed is going to be lower. So what will happen to m dot?
It's going to be lower.
It's going to be lower. So this one is going to be lower in here, so that V1 will increase. The same thrust, lower m dot, V1 increase. What does that mean, V1 increase? The change in speed will increase.
Yeah.
Okay? So whenever that speed increases, that's not good news in terms of efficiency. You know, the efficiency is 100% if Vjet is the same as V infinity, and you can check this from the equation. In order to get 1 in this ratio, this is 2, so this is 1, so this one has to be 1. So if V and Vg are the same, if the input speed and the output are the same, efficiency is 1, 100%. We know this is impossible, okay? But when we put this engine on a slower aircraft, the change in speed will even be more. So that will explain why the efficiency will go down. Is this clear?
Yes, Doctor. Thank you.
Okay. So efficiency for a turbojet is reasonable for high speeds. So turbojets are on fighter aircraft, for example, the ones that fly close to the speed of sound or even faster. Turbofans have better efficiency when the speed is slightly lower, let's say 0.8 Mach number, 0.7 turbofans are okay. That's in general, of course, there are exceptions. Turboprops would be whenever the speed regime is in the Mach number 0.6, maybe. And starting 0.5 and below, internal combustions are good in terms of efficiency. Okay, Shweb? Any questions? Okay. So this brings me to the last part of today's session, which is the summary sheet of chapter 3. If you have the textbook with you, you can open it to page 186. That's technically the last page of chapter 3, where you're going to have a one-page summary of all the equations in this chapter for the different types of engines. So these are the equations that are there for the piston engine, reciprocating engine, where it shows you the variation of the power with the velocity and altitude, and the variation of specific fuel consumption with velocity and altitude. We discussed this last time, but it's just summarized in here. Also, in the same page, we have the turbojet. What's the power and specific fuel consumption? Power is thrust multiplied by V infinity. And how would this change, each one of them, how would it change with velocity and altitude? Okay, and the same for the turbofan, which is basically the same, very close to that of the turbojets. In terms when we talk about the power, but not maybe for the specific fuel consumption, and also for the turboprop. So you can be sure that at least the equations part are going to be there in any quiz or so that you can use them. But what you have here is the variation. Many of them don't really change. So the specific fuel consumption does not, for a turboprop, does not change with the speed or with altitude. Technically constant. But the power changes. Okay, so that's a useful page. You can put a sticky note or a highlighter or whatever, so that you can use this in the homework on different quizzes. Now I can also, since we're done here, I can draw your attention that at the end of the textbook, I think right before the appendix, you will find final answers to many of the book problems. So feel free to solve any problem, and if you don't get the final answer, just get back to me. This is one way to practice in this course. Okay. I will post the answers to the homework once the deadline passes. I think that's Monday. It will be Monday, if I remember correctly. So I will post it then. And we have a quiz on chapter 2 coming next, the Monday after, Monday of week 5. So I think I'm done here. I'll just be glad to answer any of your questions. Of course, I'll post the video for your colleagues who are not able to join us. Apologize for Wednesday, we had like a very urgent meeting. Yes, well, you had a question?
Yes, doctor. For
Yes.
the homework, the deadline is Monday 12 at midnight.
Well, I think it was I think I intentionally wrote it like 11:58 p.m. That means midnight, right?
Yeah, midnight.
Okay.
Because I have 2 quizzes on Sunday and Monday. I have a quiz, so.
Oh, so you can finish the
time,
homework today. Well, finish it today. That will save you time tomorrow. Those who have submitted would tell you both problems are very short and very similar to what we have solved even today. So if you spare 30 minutes, you will solve both problems.
Inshallah.
Okay, sure. Any other questions يا شباب؟
دكتور عندي سؤال أنا بخصوص المذاكرة يعني بشكل عام.
Yes.
المعلومات بالكتاب واجد بزيادة.
صحيح.
فإي ما أدري وش يعني هل إحنا نحتاجها كلها أو في شيء نركز عليه؟ لأن أذكر أنت قلت حاول إنك تربط بين بين الديزاين اسبكتس والمعلومات هذه، يعني مو بشرط ناخذ كل شيء.
صحيح.
وش الطريقة بالضبط للمذاكرة؟
What we had in the textbook here was supposed to have like basics in aerodynamics and basics in propulsion. And next time, by the way, we'll have basics of performance. And then we will use this in chapter 6. So by nature, we must have a wide basis. For example, I cannot focus on jet engine only or propeller engine only, because in the design, you can design both. So that's why we have double the equations. Actually triple if you include turbofans, 4 times if you include turboprops. I cannot focus only on straight wings because we have swept wings. So you must know this. And so you'll see it's the same thing, same concept, but it's repeated for different scenarios, for different configurations. So whether it's straight wing or whether it is swept wing, you still have to calculate the slope A and then multiply it by the angle of attack to get CL. So if you think of it this way, you will have limited number of concepts, although you have a large number of equations. Okay, so this is for the study. In the design, what will matter there is not the equations, because we'll open the textbook and we'll find the equation. What will matter is when we do the design, you need to remember what's the effect of this problem. What's the effect of having it 3G? What's the effect of having sweep back or taper the wing? If we taper the wing, what would be the effect? So I need you, when you read, to focus on this. Don't focus on memorizing the equation. Don't worry. There will be a formula sheet. Make sure that you know how to pick the equation and use it. Okay, this is one thing. The other thing, in the quizzes, I know the reading is important for the design, but it's not practical to ask you everything in the quiz. So that's why in the quiz, I specified pages. It says from this page to that page and this page to that page and so on. Okay, because I'm picking the ones that have different ideas, different concepts, not the repeated parts. Does this answer your question?
Yes, thank you.
Okay, so try it, and I think it will be more clear after quiz number 1. But why do we need all of this? It will become clear in chapter 6 when we start with the design. Okay, Shabab. So inshallah, we will meet on Monday for our basics of performance.